Good morning, good afternoon, and good evening to everybody, to all of our listeners today live on this thought leadership sessions with Infrastructure Masons. It is my pleasure to actually bring another three guests on this session. I dubbed Sea, Earth, and Space. We're bringing you the three places where we're building data centers. And to do so, we've got three exceptional speakers that will bring you the forefront of their thought leadership. They will tell you everything about what they're doing, what they're up to, and especially why is it that they're decided to go and build data centers in the environments that they're targeting. On that note, I'm going to bring back Riley from Seabase for the first presentation of today. So let's get right into it. Hey, Riley, how are you?
Good. How you doing, Romain?
Yeah, pretty good. Look, I'm going to let you do all the introduction and all the work on that one. Seabase, I guess we know what environment you're targeting today.
Yep.
So the floor is yours.
Awesome. Really appreciate it. So, yeah, my name's Riley McAdams, co-founder and CEO of Seabase. Basically, we build modular compute pods that go on the ocean floor. And yeah, we're really targeting the water's edge. And you can see our compute pods there on the right. So the first one, you basically see a single pod, and then on the bottom there, you see what a cluster would look like. That's roughly 50 to 100 megawatts worth of pods that you could see right there. So you could see the scale immediately. And kind of just starting out, AI looks digital on the surface, but in reality, the bottlenecks are all physical. Me and my co-founder, Ali, we started on the application side. We started basically building out an agentic trading platform. We basically took that and basically saw all the bottlenecks from, AI infrastructure. We talked with colo providers, saw that they were capped on power and cooling. There's all these different bottlenecks are there in the space. Obviously on the digital side, you have models, you have agents, all this stuff, but some people don't realize that, the physical side, you have power, cooling, fiber, latency, all these different sites. These are very, very big problems. We saw it very early that, it wasn't just going to be power and cooling like everyone talks about. It's the latency, it's being able to actually put, compute near users. And we struggled with that. We were trying to test from Europe, Latin America, and it was just too inconsistent. So we kind of said, what happens if you could actually distribute intelligence? What if you could put this everywhere? So that's kind of the first idea with kind of what we were going towards. Current build patterns, everyone that's building an AI infrastructure has basically the same bottlenecks. You're trying to go power first development, you're going to have grid queues that are, 5 to 7 years long. You're going to have all the cooling pressure. You're talking multi-megawatt, gigawatt level even of cooling. And then obviously the community pressure. That's the big one. That's something that we really saw as a major issue. I have a 1.9 gigawatt data center going into basically my backyard near Chicago. That's an issue. You're going to have a lot of these people push back on it because it's going right next to, suburban areas. For someone like us, we could go into, subsea and no one can basically see anything. So it's completely different of being able to, handle some of these bottlenecks. And we really believe that the future's layered. It's not going to be just one massive campus or a couple massive campuses. It's going to be different. You also have space. You have space with sovereign storage, all the different resilience layers that they add. But at the same time, you need to have compute near users. You need to be able to be near fiber, and you need to be able to serve these AI workloads that are popping up. You're going to have billions of requests every single second going forward. You need to be able to handle that, and you need to be able to handle that everywhere, not just in one spot. And so I think the waterfront is arguably the most overlooked place basically on the planet, especially for AI infrastructure. Most people that tried to do what we're doing thought, let's just put compute in a box, put it at the seafloor and see what happens. That's just a project. That's not a deployment. That's not, a repeatable playbook. That's not what you need to be able to scale this. So we really looked at, what actually you could do at the waterfront. And you have ports, cable landing stations, you have coastal power, you have all the water access and all the restricted zones that you have security for. A lot of people look at water and say, oh, there's a lot of it. Yeah. But you also have so much land underneath that you could place things like compute pods. And a lot of people might say, oh, What about, let's just put it in the port. Let's have a floating data center there. Well, these ports all use that waterfront. They use that, but they don't use the seafloor like most people might assume. So, for our job right now is basically talking with these ports, talking with the people that, actually control these areas, and they're very receptive, very, very receptive. Ports can become part of the AI map. We know that. We talking with as many of them as we can, they all love it. These are not passive landlords. Most people think, oh, just ports, it's just logistics, but in reality, they're major cities in themselves. They focus on safety, restricted access, utilities, logistics, long-term operations, but they also need, modernization. They need the higher value infrastructure revenue, new economic development. They love new economic development. They love new ideas. They want to see it as long as it's actually good and it's going to not affect them, which is why you need to work with them. That's why what we're doing is working with all these different ports, making sure that what we're doing is going to work and going to not interfere with anything that they basically need. And so we really saw early on that, going into the ocean, yes, you have some of those, bottlenecks that you solve, but at the same time, there's so much more to it, and a lot of people know that the rack densities, they're rising. Jensen says it all the time. These rack densities are going to go up to 1 megawatt plus per rack. I mean, that's insane. At that scale, heat rejection gets so much harder, so much harder. And then you have, the water changes to the environment. If you actually go into the water, you have significant heat rejection advantages. And for us, we're really looking to focus and research into the higher coolant loop. So Rubin architecture moved to the 45-degree coolant loop, and we believe that we could even push that further with better cold plate and TIM technology, as well as using our internal IP around our cooling architecture. These are things that we see as major advantages, and something that most people don't realize is that with the higher coolant loop, you actually unlock warm water deployments, something that no one even has thought about yet. Instead of, just going up north, going into Ireland, going into, Norway area where a lot of these people think, oh, let's build there, cold water, perfect. Well, there's an issue. When you have inference, it needs to be distributed. Well, with the higher coolant loop, you actually allow for, warm water deployments. You can reject heat at a high level, megawatt level on a per pod basis for us in even warm water. I mean, it unlocks significant distribution advantages that basically no one else has. I mean, try and build a data center in Latin America, a very large one. It's very difficult. It's a very hot climate, warm climate, humid. You have major issues when you're trying to use evaporative cooling or whatever it might be. Same thing for Southeast Asia. A lot of these different places that you have major AI demand, yet it's a warm climate. It's very hard to build it. So that's kind of what we're doing, is we're basically looking to go into everywhere in the world, warm water, cold water, and be able to deploy our pods and be able to actually serve AI workloads at a high level. And the real-time workloads are going to love us because we can actually be right there near the data, near the people, and that's perfect. You have everything that you need for, real-time workloads to go at a high level, and you have increased higher throughput, which then you lower your cost per token. So, I mean, the overall advantage, it just continues to compound and compound as you actually, look deeper into it. And so, Seabase, we're obviously building the ocean layer for AI infrastructure. Not one pod. We're trying to build a repeatable deployment playbook. For investors, this is the next physical layer of AI infrastructure. For operators, this is dense inference near coastal demand, right near where everyone is. You have over 50% of the world that lives right on the coast. That's where the demand is. If you could do something with the water, you don't have any issues with NIMBY, nothing like that. You could just go in there, you could serve the workloads, and then you could scale up with demand or modular. We see, demand's obviously accelerating, but you don't know where it's going to be, how big, or anything. So going modular allows us to scale up with demand, be able to build these clusters where we actually need them, and then scale up, megawatt by megawatt instead of just building, 2 gigawatts and maybe people will come. That's not our business. And so, yeah, we would actually like anyone in the audience to actually scan the latency map, if you would. And that kind of shows more or less what we're looking for this major inference network that we're looking to build out. You'll be able to see basically any port in the world, what the latency equation would look like versus these major clouds that you're basically only going to see in the US, a couple of small data centers down south, maybe in Southeast Asia, but these clouds, they can't just build, everywhere. They're trying to focus on training. They're trying to focus on batch workloads. It's very hard to just build modular and do all that stuff at the same time of building, gigawatt level. So for us, our focus is inference, pretty much inference only, and being able to scale this worldwide and distribute it as much as we can. And the latency map really shows that. But nonetheless, we really appreciate the time. Thank you, iMasons.
Riley, thank you very much for that presentation. Really fascinating to see your approach, and especially the tidy up of linking where the demand is going to go and the existing infrastructure and the support that they're bringing to you. We'll bring you back in just about 20 minutes. We've got 2 other speakers to bring on first, so awesome. So thanks for that. And next into line, we've got Duhita. Duhita is working for Crusoe. She'll explain exactly what she does. She's got a fantastic presentation for us today. Really looking forward to that one as well. And we're going to be talking automation and robotics. Duhita, the floor is yours.
Awesome. Thanks so much, Roman. Hello, everyone. Good morning. Duhita again, and super happy to be here at the iMasons panel. A quick background on myself. I have worked in the construction industry for about 10 years now. A vast majority of that was with DPR construction, mostly as a project manager with some exposure to pre-con, with design management, and my projects included data centers, life science projects, as well as some healthcare projects. Fast forward now, 6 months with Crusoe. I work on the pre-con team, and primarily my role is to work cross-functionally within Crusoe teams. That includes real estate, power, energy, controls, and construction operations to essentially align on the design intent, align on the project budgets and schedules up until the handoff from pre-con to operation happens. Okay, I covered my background. Okay, now moving on. Here at Crusoe, we are looking to build large data centers, of course, on the land. And the biggest challenge that we are seeing right now is to essentially deploy skilled labor on the construction sites. You must have already heard some of the job sites that get selected for these data centers on land right now are so remote that looking to deploy approximately 3,000 to 5,000 people on those remote job sites is a big gap right now. The other thing that we are looking at is the scale of these hyperscalers is so large, and then the speed, given how much compute is needed at this point, the speed to deploy these infrastructure projects, we're on an average, we're looking at 18 to 26 months average build time for these campuses. So we're looking at basically same teams, approximately 10x the output, and of course data centers are not an easy environment. So deploying these people on those sites at significantly higher risk is like another problem that we are seeing. Moving on now, taking a little bit of deeper dive into how are we looking to solve these problems. So as Romain mentioned earlier, like automation is of course one of our key focus areas, and out of many examples, just some of the examples that I'm looking to highlight here are within these 3 domains to basically automate the processes. So beginning with construction equipment operators. So now the current challenge is because these sites are so remote, the problem is having unstructured terrain. So looking to have some autonomy in using construction equipment like excavators or similar equipment to solve that problem. And then of course the KPIs would be like, we're looking to see how many dig cycles per hour can the equipment achieve. That is an area we are exploring right now. In terms of welding operations, also given how much structural steel goes into these big infrastructure projects, looking to see the high mix, how can we achieve what quality of weld can we achieve in the first pass? What quality of yield that does the first pass of the welding would give us? That is another area. Again, these are just a few examples of many challenges that we are seeing that I'm looking to focus right now. Lastly, surface finishers. So given the scale of these projects, these are massive, right? And fun fact, the Stargate at Abilene is larger than Central Park. So given how much floor area we have, we are looking to see how can we automate the floor flattening and floor leveling processes. Again, another high mix area. So how much productivity can we achieve in a square foot per hour is a focus. Again, there are a lot of other problems, but these are like what we are focusing right now currently at this time. Now, how are we approaching this? Of course, automation. So manipulators, teleoperation, humanoid parts, these are already coming. Definitely looking to explore those areas. Could we have a fleet of robots? Absolutely. Can we have these complex system of network working 24 hours on job sites to achieve the productivity, to achieve the timeline that we are looking to build, and also thereby increasing productivity by augmenting the workers. Work is another area we are looking into. And then, of course, risk mitigation, given the hazards. Of course, keeping people away from the hazards is and if we can achieve that, it would be a great solution. So safety, compliance, and then predictable outcomes. Again, given the timelines are so tight, we want to have those predictable outcomes. Now, what this means for the industry, of course, the labor shortage is a real problem, so automation is not at all an optional thing. Given that we are exploring robotics and automation, the goal is not to take away jobs from people, but to actually augment the workers. So we want the bots to do the task while people, human beings, do the actual jobs. Now, AI and robotics is not just in our way or blocking our way, but it's actually unlocking so many more opportunities in multiple trades. And these complex systems are actually, the point is, can we train these complex systems so that they can operate 24/7 on such a remote job site? And mobility and manipulation, of course, are one of the avenues and core capabilities that are needed for these machines to interact with the real world. That's all. Thank you so much. Again, when we are exploring these areas, anyone from the audience would like to connect and talk about it further, please reach out. We are totally happy to continue this discussion further.
And thank you, Duhita. A fantastic example of the innovation going on within your company, actually, and a number of reasons why automation is actually needed at this point in time. Before we jump onto the panel, we've got one last speaker for you. I would like to welcome to the floor Chris Stott from Lone Star Space. Hey, Chris, how are you?
Doing good, Romain. Thank you very much. And thank you, iMasons, for having me too.
It's an absolute pleasure. We got connected randomly about a month ago, and what a learning experience that's been for me to actually come and understand what you do. I'm not going to steal your thunder. You've got plenty of store for us, so we're going to leave you to it, and then we're going to bring back the other speakers right after your presentation.
Well, thank you, Romain. And again, thank you, everyone at iMasons. We've been looking forward to this. And I love the lineup you have today. I mean, from robotics, underwater data centers to data centers in space, focused on sovereign storage. Thank you, Riley. I saw that. That was very cool. And all we're all doing is focusing on that four-letter word, data. Providing data, looking after data, curating it, storing it, generating it in ways to meet this tremendous demand that we're facing in our industry, a demand that doesn't ever look like it's going to slow down. And I don't say that lightly. So at Lone Star, we've put 4 data centers in space already, 2 up to the space station and 2 on the moon itself. And our next commercial mission heads up next April, fully commercially operational. Now, rather than me tell you about this, how about I show you? Sometimes, images speak louder than words. So I've got a video to show you. And guys, could you cue the video?
I'm retired NASA astronaut Nicole Stott. And together, we are Lone Star. We live in an age of digital wonder. We are experiencing a digital renaissance. Every day, the human race creates over 600 quintillion bytes of new information. That's 600 exabytes of new data every 24 hours. Over 600,000 petabytes more than yesterday. And the rate of creation is growing exponentially, on track to reach 1 zettabyte a day by 2027. The data we create drives every aspect of our lives. More, it is the very beating heart of our technological civilization. Yet, while that data is so vital, it is also increasingly fragile. As its value continues to increase, the more at risk it becomes from loss, from theft, from network intrusions to nation-state attacks, from natural disasters to climate change, from human error to ransomware. We are at serious risk of losing the data that literally runs our modern world and is the foundation of our everyday lives. So what if we could do something about this? Well, now we can. Lone Star is working to save all our data by building the world's first global data storage network in space, a cloud above the clouds. From Earth to the moon, a new layer of secure infrastructure, providing petabytes of secure, sovereign data storage. Space allows Lone Star to leverage the benefits of uninterruptible power and free cooling, and to leverage the unique geography of space to provide service to every nation on Earth via secure, line-of-sight broadband communications. Yet, the ultimate advantage comes from Lone Star's application of space law to ensure the unparalleled sovereignty of its Star Vault data embassies, not possible on Earth. How are we doing this? By building on 60 years of return on investment, from development and operations associated with space exploration and Silicon Valley. By building a team drawn from the very best of the data center and satellite industries. Together, we have successfully tested all the necessary hardware and software for our missions on 2 flights to the International Space Station and already 2 to the moon itself. The time for testing is over, and we are now moving to our first fully commercial operational missions, a series of Lone Star Star Vaults to fly as hosted payloads in a proliferated orbit strategy to provide commercial service to our customers. Our next mission launches in April 2027 from Vandenberg Space Force Base, with SpaceX flying on a Sidus LizzieSat-4 with 500 terabytes of capacity, followed soon thereafter by a series of multi-petabyte Star Vaults in all Earth orbits. Then, in 2028, with our first generation of 100 petabyte data embassy Star Vaults headed to the L1 Lagrange point, a strategic orbital location between the Earth and the moon, all leading to our return to the moon, a place so perfect for data storage, if it wasn't there, we'd have to build it, allowing us to expand our secure global data storage network to exabyte, zettabyte, and on to yottabyte level capacity for data housed safely, securely, accessibly in the moon. The ultimate backup for our planet's most critical data. Lone Star, saving Earth's data one byte at a time.
So Romain, everyone, thank you. That's Lone Star in a nice brief video. And that next mission goes up in April. Looking forward to it, fully commercially operational. And we're already signing customers, multi-year customers, what they call annual repeatable revenue, which is fantastic. Going from test to reality, having our test customers come on board as full-time commercial customers, fully operational. If you're interested, give us a call. But that's us. That's data storage in space.
Thank you very much for the video. I really appreciate it. You made actually, just to finish on your presentation, a comparison between land data centers and space data centers. Do you want to take us through that before we bring back everybody in the room?
Yes, please. Thank you. That's a really good point too. So our team are drawn from the data center industry and the space and satellite industry. I myself have been in the satellite communications and launch vehicle industry for over 30 years. And this was the biggest shock to me. It was realization of both of our teams when we started really working together and talking together. A data center is a satellite just on the ground. A satellite is a data center just in space. You know, Sputnik went up in 1957. We've been doing this for 69 years without really realizing how similar they are. They both come from the same source code out in Silicon Valley. It's fascinating, right? In the data center world, we talk about gray space and white space. Gray space, power, thermal, communications, management to look after the white space where we make the money, the racks. In space, we have the same exact conversation about the same physical functions. We just give them slightly different names. So on a satellite in space, power, thermal communications, the gray space, is managed by our solar panels, also powered, batteries for backup. Oh, wow, 2 independent sources of power, fantastic. And our thermal management on the spacecraft buses with radiators moving the heat, power around. And of course, our communications, we don't have cable fibers connecting us in space, but we do have satellite antennas with radio spectrum backwards and forwards and laser links in between satellites. But the more we looked at this, that's when this big light bulb went off, because we get a lot of questions about, hey, as data centers in space, how are they going to do this? Well, no one's taking those massive data centers into space. What we're doing is taking the electronics and shielding them and doing all sorts of wonderful things. But it's fascinating, isn't it? How the two can be so totally the same. Even with underwater data centers, how the two can be totally the same, right? It's just the electronics in a different location being powered and cooled. So this was huge. But of course, when you put, like, say, sovereign storage in space, not only do you get the free power and free cooling, same capital costs, ladies and gentlemen. But what's interesting is the view. Because of space law and data sovereignty laws, space law, the hardest thing about getting into space is actually getting permission. Like I said, we've been doing the rockets for about 69 years. All of a sudden, we get a global view. We can actually go to the global marketplace with data sovereignty laws and hosted payloads and data embassies. So for us, space works out really, really well. But for us, a satellite is a data center, and a data center is a satellite just on the ground.
That was brilliant. Chris, thanks. Yeah, thanks very much for taking us through this. I'll tell you what, we'll bring back everybody in just a few seconds, and we'll walk right into a panel. I can see that the comments have been pouring in already, so we're going to hopefully have enough time to go through all the questions. But thanks very much, everybody. Keep them coming. I can see answers flowing back and forth already. This is exactly what those sessions are about. Thanks very much to the 3 speakers for that wonderful introduction into today's topic. And let's get right into the panel. Riley, Dahita, Chris, well, we'll come back. It's a wonderful journey from the depth of the sea all the way to space. It's fascinating to see how things are changing. I remember not that long ago that we were talking about traditional buildings being data centers with a bit of IT equipment, and now we're just pushing the boundaries of what's possible and what people want. Let me open up with a cross questions to all of you. Are you all competitors or collaborators?
Oh, I'd say collaborators very much. Our focus is storage and space. If the others agree, I'm just throwing that out there.
Yep. What? Duhita, Riley, what's your take? Are you going to be fighting for the same customers? Are you all building a background of infrastructure that will serve the same customers in different way? What's the story behind the fact that we go at the depth of the sea in space and continue to expand the data centers on land?
Not competitors, definitely. It's definitely collaborative. Again, the requirements, the specifications are so specific depending on customers and what they need and what they're looking for. So that definitely puts us in the collaboration mode.
I'm going to take some of the questions that came through, and some of them were very, very interesting. We've got a question from Maria. That said, for each of the speakers, what phase of innovation are you in? Ideations, lab prototypes, pilots. What's the take on it? And even if you have things in play already, data centers that are live, storage in space that's live, do you continue ideating, prototyping, and doing pilots?
Yeah, I can take this one. So in terms of Crusoe, right now we are, I would say, ideation and pilots both. We've got some ideas, we've got some initial preliminary conversations, and also we've got some proof of concepts happening right now as we speak. So ideation and pilots ongoing.
For Seabase, we're in the final stage of basically your design phase, starting permitting pathways, basically talking with as many ports, CLS as possible, talking with also colo providers, talking about basically IXPs, carrier hotels, trying to basically get ingrained into that, kind of basically set up that we're more of an extension to kind of what already exists. So that's kind of where we're at, is really starting to get all the relationships built. Also, we have our IP portfolio that's already built out. More or less, we're starting to get into the prototyping phase, kind of laying out that, getting basically vendors and the right partners in place to have this all built out.
And with ourselves, we always listen to the customers. We're constantly updating our service offering, adding new services for customers. We had some customers approach us about space-based compute recently, which we're able to do because we keep compute on board to look after the storage. IP portfolio, 1 granted, 4 in process, and a whole bunch more coming because we're constantly learning, but we are now actively deploying. So we're past our test phase and doing the actual commercial deployment with customers, which is wonderful. Makes me very relaxed on one level. On the other level, we better do what we're going to do.
There is an element, both from the automation for yourself, Duhita, as much as deploying environments in what I would maybe called inaccessible environments underwater in space, where you better get it right first because you can't just go back and change it. How does that work through the innovation process and the design process? What steps do you take to make sure that things are done right the first time?
Well, can I jump in on this one? And then, so for the space industry, this is what we're used to. We're used to building amazing electronics and putting them in that harsh environment of space. So it's all about testing. It's about triple redundancy. It's about solid supply chain. And then as we go forward as well, I mean, given the change in storage density on storage devices, SSDs, we're actually following the traditional terrestrial data center industry on modular design. The idea being that we're constantly building and replenishing and sending things backwards and forwards on a 5-year cycle for us. And so that's how we're maintaining that innovation, keeping track of the marketplace. But also for the space guys, we test again. There's an old saying, A guy called Jay Honeycutt, who's on our advisory board, Presidential Medal of Freedom winner for saving Apollo 13 and former president of Lockheed Martin Space Operations. Jay says it's always better to be down here wishing you were up there than to be up there wishing you were down here. So lots more testing.
That's a very fair point. What about yourself, Tuhita?
Yeah, I mean, given that these scopes are so large, absolutely, you're hitting on the right point that we cannot afford rework because that will involve so much time and money. So to get this process right the first time, I think going into the nitty-gritty of truly understanding the product and the need for what the projects are, for what the scopes are essentially looking for, and taking the time to iterate multiple times in various different scenarios to be able to get to the final point is something I would say that's the way we are trying to achieve that. Just multiple iterations before finalizing or locking anything down.
Yeah,
What
for
about yourself,
Seabase, so we're looking at a couple different test sites, ideally using pools to kind of start. There's a couple different facilities that actually have really good technology to basically change different flow, different temps. So ideally, we're looking to get into one of these test facilities. And actually, it's cool because we're able to test different temps, flows that are all over the world. So if we wanted to go into Mumbai, for example, we could effectively take the ambient temps, take the ambient flow, and effectively send that back to this facility, and then actually simulate that data. We actually are partnering with UConn right now to work on like CFD, digital twins, to basically kind of build that out and kind of make sure that, it's not just that this is going to work at a high level, but also the economic impact, ecological impact is not going to be affected. Wildlife's not going to have any issues. And just for example, a lot of people assume that vibrations are going to be an issue. You have, these massive wind turbines that are obviously generating a ton of vibration. For us, we have all of the compute internal, and we're actually able to remove that vibration. So the wildlife actually will love what we're building. So that's kind of what we're focused on.
Wonderful. Thanks very much for taking us through this.
So for the maintenance, it's definitely a good question. Right now, we actually have patent pending foundation system that allows for much easier lifting and dropping onto the seafloor. But we also, because we're close to these ports are experts, arguably the best in the world at logistics, at anything basically with marine engineering. So actually, they're going to be able to assist us with, using these massive vessels or, mid-sized vessels to go to this deployment area and actually lift up these vessels, bring them back to the port, do everything that we need. We have a deal in place with CDS.net. That's one of the biggest maintenance providers for data centers in the world. They get to one of our deployments within 4 hours and be able to maintain just about any equipment that we need. So if something breaks, definitely an issue. But we've thought about that constantly. We have a lot of different solutions for that.
I'll bring the question to you as well, Chris, because once it's up there, what's the maintenance like? What can you do actually from the ground to continue maintaining the satellites and making sure that they work correctly?
Oh, no, thank you. Yeah, great question. Same thing with us. We do all the testing on the ground. We have a mission control, which we operated last year for our last mission to the moon, where we're constantly monitoring the drives, the health of the vehicle. This is normal in the space industry. We routinely build big geostationary satellites the size of small houses full of electronics and put them up in space for 15 to 20 years. It's rare for a failure in space, but that's where the triple redundancy comes in. We sadly don't send astronauts to go change out drives or anything like that. We have several astronauts working with us, and they've all volunteered to do it. Literally astronauts working from Apollo moonlanders to spacewalkers and people who live on the space station. And they're like, "Oh, we'd love to do that." I'm like, "Yeah." But that's why we have the redundancy in many units up there. And so that's how we do it. That's how we do it in the space and satellite industry. Really good supply chain. And if something fails, we also keep backups on board too.
So you're talking about a 15 to 20 year lifespan. Do you go as far as think?
No, we're 5 years. We're a 5 year lifespan, so we can, because they keep up track of Moore's law. But some of the big satellites do 15 to 20 years up there up a geostationary
Okay.
orbit in sun. But they've worked very well to date.
So a bit of a follow-up question on this, because I believe this is the same for the three topics we've had today. What happens for end of life cycle, and how does it work?
Oh, in space, it's strictly regulated. And so we do all of our work through the United States and the United Kingdom, the two largest commercial providers of space licensing and space operations. So by law, at the end of life of our satellites, or the satellites that we're flying on, they must have a plan to deorbit safely. We have a plan to wipe the drives, move the data to the next device that's on orbit as well. And so that they come in and they burn up. We're working in low Earth orbit for this next mission, so it would burn up safely in the atmosphere. And so, no, it's incredibly regulated. It's not like that movie Gravity. It's so when people like SpaceX are putting 1 million data center satellites up, it seems like a lot, but there's a lot of room in space. Heavily regulated. Better than air traffic control at Atlanta Airport on a busy Friday afternoon.
And I'll ask you the same question for you, Dahita, because a lot of the automations you're talking about are for constructions. Constructions are based on projects. So what's the plan on redeploying those resources for the next project? How is that actually looked at? Is it just a one-off and then discard? Is it we deploy it there and then redeploy for the next project? How did you conceive it?
Yeah, no, great question. There is so much planning that goes into it from one project to another. Definitely, it's not something that one off and done and discard. It's definitely redirecting to as much as possible to whatever makes sense on when we move on to the next project. So yeah, it's very lots of planning and lots of redirection instead of discard. Definitely, it's not going to be 100%, but there's a lot of effort and planning to take whatever we can and just reroute it, to redirect it.
For Seabase, yeah, I mean, so this environment's definitely different. A lot of people might assume that corrosion is going to just destroy everything, but that's actually not true. Basically, in marine engineering, there's different metals that you could use to basically keep these pods that we call them actually to last about 20 to 25 years, possibly 30 plus. So ideally, we're looking to basically design a internal kit that could kind of be swapped in and out. So as chip architectures change, you know, all these different things are obviously accelerating. So we obviously want to be able to keep, you know, the main shell as long term as we can, and then basically input, you know, new kits when we can. And then at the same time, this foundation system I just mentioned a couple minutes ago, basically it sits on mooring blocks, which are effectively, you know, very, very easy to permit compared to many other things for offshore. And so these foundations basically sit on mooring blocks instead of the actual seafloor. So end of life is actually pretty easy to, you know, remove the foundation, remove the pods, and basically looked as if nothing ever was there. You know, a lot of people look at subsea fiber lines, you know, that's pretty much where we're looking to kind of go in on the permitting side, is just sliding in under already basically permitted areas that have fiber lines, that already have the navigational waters already organized. You know, everything basically that we're doing is really just piggybacking off of what already exists, which ports, you know, they permitted all this stuff, you know, fiber landing stations, they've all permitted, you know, basically what we're doing outside of just the foundation system. And that's basically what we're working on with regulators, is how do we actually get this permitted properly? And then once it's permitted properly, then you can scale this out like it's a brand new architecture, similar to parking spots. That's kind of how we look at it, is, you know, these foundation systems are going to be really easy for end of life recovery and just basically be a subsea parking spot for AI infrastructure, and immediately be able to connect into nearby ports, CLSs, whatever you really need to basically have that fiber that you really need to be able to have in, you know, massive bandwidth. So yeah.
Perfect. There has been, I think we've pretty much gotten through all of the questions. There was one about environment, and I'd love to get the three views. I'll start with you, Chris. Is there any environmental concerns around putting storage in space? The whole chain, maybe launching the rockets. What's your view on, like, and how do you consider the environment through a business like this one?
No, thank you. The environment is massively important to us. There's no point in saving all of Earth's data if there's no Earth left to save. So we run it carbon neutral. We want to be carbon negative. One of our carbon sequestration partners has planted 1 million corals. So, Riley, we should chat. We actually
Yeah.
help rebuild reefs, right? I mean, because that's how you sequester carbon. We actually are absolutely focused on our type 1, 2, and 3 carbon. We do that with all of our providers. And we even have SpaceX's type 1 carbon as well for our launches. And so we look at that. And then when we're in space, we're environmentally very, very sound. We are running 100% on solar energy, natural cooling. We even generate carbon credits. So that for us, it's a huge thing. I mean, for all of us, right? I mean, this is about handling this tsunami of data that's coming towards us. And this is a high technology problem with a high technology solution. And that's okay in the 21st century. But the environment, every single step of what we do. And it's, again, that regulatory compliance and that moral and ethical compliance as well.
So can you mentioned carbon credit? Can you take us through a bit more of the details of what that means, especially in your environment?
Absolutely. So we've already been approached by the New York International Carbon Exchange. And what they're realizing is when you put a data center up in space and you're running on clean energy, and you can actually show that the computer's operating this way and the storage is operating this way, we qualify for carbon credits, type 1 carbon credits. Now we have to be able to show this, monitor it, meter it, which we can do. We're a satellite. We have that TT&C tracking telemetry and command coming 24 hours a day in and out of our mission controls. Fascinating, right? So especially when we're working with our European partners in the European Union, where they are required to have type 1 carbon credits generated. It works out very interesting conversation.
Riley, up to you. What are the impact on the environment? What are the studies showing you about putting data centers at the bottom of the sea? I'm not sure if Riley can hear me.
So on the impact for the environment, I kind of touched a little bit on it. For us, we do also have a partner with someone that's building out synthetic reefs. So ideally, the fish that we've kind of modeled out actually are going to pretty much treat it as if we're building synthetic reefs. This generates a little bit of heat, and since they're isolated units, we're not building some monolithic, massive data center that's, radiating just right there. So we'd actually spread out our pods, to make sure that there's no damage or anything like that, and that, fish are actually going to enjoy this area. And yeah, obviously we're not going to put these right next to a reef, that would be really dumb. So obviously we're, site planning is something top of mind for us, making sure that it's the right area. There's going to be no environmental impact that's going to obviously hurt everyone. And yeah, ideally we really want to push eco-friendly and be able to test these places that we're going to go into well before we actually put something in the water there. So, the test facilities that we're looking at are really going to be, very important to what we're doing and making sure that there is no, impact on the environment that we didn't expect. So that's kind of what we're looking for.
Brilliant. Thank you very much, Riley. Dimitri, final question for you. We're talking about a lot of automation being put. We've seen the gap in the human capital that actually goes into building those data centers. We're trying to pull out that human capital. How realistic is it that we can? We're talking about 1 million people trying to compensate for the lack of resources and skills going into building those data centers. Based on the plans that you've seen, how realistic is it that we can actually compensate for those lacks? And how quickly do you think that's going to be in effect?
So to understand your question correctly, you're asking what's the plan to get the specialized talent on site before we hit the ground running?
Yeah, so you've mentioned in your presentation that there is about 1 million people gap of skill set. You're talking about bringing innovation, automation, robotics into the sites to compensate for the lack of skills. How much of an impact do you think the current state of automation and robotics can plug that gap?
I think there is a lot of scope there for automation to even fill out that gap, because the reason being we're already in partnership with some of these robotic solutions. For example, one of the examples I can share here is bedrock robotics. So they're essentially they're looking to automate utilizing excavators, and if we are able to deploy more than one equipment, like a fleet of robots, as I was mentioning before, the gap will be reduced much faster. At this point in time, we are definitely partnered with them, working with them. There's a proof of concept ongoing on one of our job sites. So yeah, I don't see it being too long to be able to bridge that gap. It's coming. It's already there. It's getting there, and there's a lot of efforts and push towards it. A lot of um, resources being put around that to be able to solve that problem, Romain. So yeah, I don't see it being too long.
I could also see in the comments earlier that somebody was asking to show what the robotics looks like. I know we haven't prepared for that, so I'll let you do that. And I would strongly suggest that anybody interested in any of the three topics that we've had today, reach out directly to our speakers. What we're going to do, I can't believe we're already running out of time and we're getting to the end of the hour. It's been actually fantastic to contrast and compare in the different environments, to being able to unpick the different elements of that infrastructure. But just a final few words from me for today. First of all, Chris, Riley, Duhita, thank you very much for your time, your efforts, and your preparation in bringing all those presentations together. It's been fantastic to learn about it.
Well, thank you very much for having us. Come fly your data with us.
And for anybody who wants to actually attend the next ones, we've got actually on our website, imasons.org/events, you will be able to find all of the next series, either on Meet the Startups for all the startups that we support and integrate into the environment through our accelerator, but also for all of the panelists like today that come and share all of their thought leadership. If you've got any questions, come back to us at innovation@imasons.org. That's the best and simplest way to actually come and ask us questions for anything that you want to do or any activities that we've got ongoing. And if you ever want to be part of what we're up to, have us kind of the QR code here. You'll be able to figure out all of our working groups, the different events that we put together, the documents that we edit through our working groups, and all the content that we put out. Including our pitch competitions to actually come on a regular basis. On that note, once again, I'm very pleased that we could have you three on the call today and present to our fantastic audience. And we hope to have you again very, very, very soon. Thank you very much.
Thank you.